Sorry, I meant to record this, so I'm going to record this again. So basically, in we have variable 1, variable 3 not initialized, but variable 4 and 2 initialized when they are declared. Now, in the main function, we understand why we use main function from a couple of weeks ago, those who were in class. In the main function, basically, we initialize the transmit signal, we set the baud rate, and then we define each variable in the order. So variable 1 has the value 1, and variable 3, 3, 2, 2, and 4, 4. Then this is the reason why I use this function. It's a memory dump function which sets the range. Look into the address range 100 all the way to address range 08FF, which is the stack range that we talked about. The rest we can choose not to worry about it for now, but as you understand and look into it, you will really understand what is going on. This is simply referencing and dereferencing to get the actual pass the actual address across. And then here, remember when we did the writing to the serial monitor, when we simply wrote it, we got the ASCII version. So this is how we convert it to basically we convert into hex, and then at this point we simply print to the serial monitor. So that's just a brief overview. We're getting the data, and then we simply printing our variables to the serial monitor by using this function called memory dump function. So all we have, we do not have any other functions. It's just the memory dump, and then we simply dump in what is memory, what is done. And then the while one, obviously, will put it in a constant loop when the main function runs to stay there. So those who were confused at the beginning, that's what is happening. Let's look at the serial monitor's output. Now, what I will say now, obviously, this circuit is simply sitting there doing nothing. It's just progressive to the stuff that I've been building or what I used for the tutorials or some stuff that you've learned. But at least it puts the Arduino there so we can program it. Serial monitor on the Tinkercad is actually limited by the number of lines it can print. So I'm going to start and stop it. What I mean by it is if I run through it right now, it's going to print all the way, but eventually it scrolls up when it reaches the maximum and you won't see what is happening. But that is not what we are after. We are after something special. So we will pause it at the right address so we can actually see this. This goes all the way to 08FF address. That's the last address, whilst the 100-bit has cleared off. So what I'm going to do, I've cleared the screen. I start the simulation again, and I will stop it right at the top. So start, and I'm going to stop it here. So we've got the dot data, which is the value for the initialized value, and then the dot BSS for the uninitialized value. How do we interpret this? So basically, we notice that variable 1, which is 111, the variable was not initialized when it was declared. But variable 2, which is 2222, was initialized to a random number B. But it is long. So when you look in memory, we have 4 bytes here. So this is 1 byte, 2 bytes, 3 bytes, 4 bytes. So 4 bytes representing one variable. So now we're digging a bit deeper, right? So that variable is declared, but obviously initialized. And variable 4 is also declared and initialized. So hence, variable 4 gets printed in the data session. And once we have the data session done, the dot data session, we go to the dot BSS. So the uninitialized one, which one was initialized first? That is 1, and that comes first. And then which one was initialized second in the main function? That is 3. So 3 gets coordinate. So this shows that even though in the main function, even though we in the main function we initialized, we assigned variable 1 first, or in that order, to variable 4. In memory, they do not appear to be the same. The ones that were initialized during declaration gets put in the data, and the ones that were not initialized actually gets put in the .bss. So let's say if you have your assignment and you are working on it and you want to show off a little bit after you implement your stuff, you can use this code, the memory dump code. All you need is the memory dump code. You use the memory dump code to show what is happening in memory. You take a snapshot of this. Those asking what goes into your report, you take a snapshot of this, you put in your report, you give me an analysis of it to show that you really understand what is going on in memory. You understand your code. It's not about copying code from the internet to make it work. You understand your code, you know what is happening, you know what is where and how what is what, and you know why your code is probably the most efficient version, that memory efficient version you can write and submit for that particular assignment. Okay, all good. Any question, please ask. No question, I will assume that you understand what is happening. So stuff like this to ensure that whilst there's no data to send, move on. Whilst there's no data to send, move on. Okay, so no question for me. I can go back and talk about other stuff as well. So that takes me away from SRAM. For SRAM 1, let me move to project, and I will move that to the advanced Arduino stuff. And the same for S1 too. Just doing this so you see how I move stuff to project. When you're doing the assignment, you can simply create a project for it and your stuff there. Okay, so we are interested in this particular one now. You don't have SRAM 2 yet, but it's pretty much similar code. We're going to walk through it really quickly. Guys, do you have any question for me? Please, if you have a question, type it in the chat window. Otherwise, I'm going to carry on assuming you're okay with it. And remember, I'm not repeating this. You have to basically try to watch the video to understand it, right? So a bit more, and we want to find out what is happening in the stack, right? Remember last week we talked about stack. It's like putting coins on top of each other. First in is the last one out, and then the stack grows towards a smaller number. So stack grows to become a young person, right? So this is pretty much the same code as we saw before. Like I said, this is my code I've written from scratch, but it helps to tell the concept. You can pretty much change this yourself to anything. So basically, four bytes long, and then you have a byte where each of these data is each of these entry is byte long. Then we put some ridiculously large number, which is about 240 byte entries that we are expecting for one array, and about 256 entries we are expecting for another array. Similar as before, initialize the serial transmitter and then set it to 57,000 or 56,000 version of the serial baud rate that we are working with. But what we note is that obviously there is some info for you that as you add, you can double check this in your Arduino code, but when you add these arrays, because the arrays are ridiculously huge, you increase the memory size to 512. Anyway, so the same code as we had before, variable 2 and 3 are initialized, and then also we assign all the variables in the main function. Okay, now in order to have some tangible data or some real data, we set the first element of this particular array to some random number, and then we set the last element to some random number, the same. So the same way we set that for the second array and then the third array. And remember, the stack, when you call a subroutine, the elements of that subroutine will be put in the stack. So basically, when this subroutine runs, the variables will be put in the stack, and then it will be emptied when the function finishes, ready for this particular function to write. Let's remember. So we've got two functions where we have the first function and then we have the second function. Now the memory dump function is what dumps the memory. So basically, first of all, before we were doing the memory dump from here, from the main function, so we were not really seeing anything with variables or local variables to functions, because we were not using any functions at all. Right, so now we do the memory dump from the subroutine. Does it have to be the same format? So basically the array, it can be any hexadecimal number, but remember we are using a byte, which is 2 nibbles. That is why we use these numbers, but it can be any number as long as your syntax is correct, right? So this one is 4 bytes long because you defined it to be 4 bytes. So at this point, you're beginning to demonstrate that you understand everything that we've been doing in class so far, right? From the data types and other things, you're bringing all those skills into play. Anyway, so back to the point. We do the memory dump from the first subroutine, and in the first subroutine, we have 2 variables. So the variable that we have, let's say, where are the arrays? We've got array 1, array 2, and then we have in the function, we've got this particular arrays that we call, we initialize a value of b to the first variable, and then c to the second variable. So it's just an array that we are assigning, and we are filling all of them in this particular case. So in function 1, we are looking at in subroutine 1, function 1, we are looking at B and C as the local variables, and in subroutine 2, we are looking at D and E in the local variables. Guys, if you don't mind, I may just go over just by 2 or 3 minutes, and we do have another class to jump to. This is quite important for you to understand because it can be a bit tricky. Now, what we know is that we want to go all the way to the end for the stack. If you look at the drawings that we had a look at earlier, the stack is at the bottom. And if this will allow me to pull it up, but because Thinkercad does not show everything, I will let it run all the way to the end. We can stop it at the right time though. It's going to run. Then we notice at the bottom, we should expect B and C to pop up very soon. So suddenly you see B, and then C printed at the end. So the B has scrolled down a bit more, and because this is the stack grows towards a younger number or younger address. Originally, the stack pointer points towards the bottom, and then when you push B in, B goes up, and when you push C in, C goes up, and then it makes room for the next function to run. So this is when this function is running. See the stack at the bottom. Remember, the stack is at the bottom, so the stack is growing towards the .bss, and the .bss is also growing towards the stack, which is what we have illustrated here. So let's make some changes. So what change can we make? The change that we can actually make is basically we can call, get rid of this, and we can call the memory dump from the subroutine 2. So if we call the memory dump from subroutine 2, go back there. Yeah, remember the first subroutine runs and make room for the second subroutine. Are we all happy for me to go on for just about 2 minutes? If so, please show a smiley face and I will go on. Brilliant. So we carry on then. Right. So if now we are actually calling the memory dump from the second subroutine, so we should expect the first subroutine to run and then free the C and the B variables and to make room for the D and then E variables. So at the beginning, the .bss and the data and .bss get printed, and then we have a lot of other parts of memory that we are not seeing. Print, then go all the way to the bottom. That is when the stack will also start printing pretty much very soon. So suddenly we see D being printed and then E being printed, skipping the B and C altogether because the B the B, C, D local variables of this subroutine has been freed to make room for the local variables of the second subroutine. So let's see if this is right or this actually works by, yes, of course, because the subroutine finished. So we need to make room for other things to run. So let's run the second, let's call the second subroutine from the first subroutine. So what that means is that when the second subroutine is called a nested subroutine or nested loop or nested functions. I don't know why I keep saving, because I think I'm programming in Arduino. Right? When the second subroutine is called from this first subroutine, at that point, this has not closed. So the first subroutine is still running. The second subroutine will run and finish before the first subroutine finishes. And remember, we are calling the memory dump from the second subroutine. So at that point, B and C has not been freed, but they've just been pushed up towards the .bss. So because sadly Tinkercad clears the screen, it has a limited monitor view, but we will understand because we've got a figurative view. So let's start this simulation and see what happens. So data.bss print 0 0 0 0 0. I'm going to stop it first time I see the B and then the C. And so we've got D, E, B, and then C being printed. The same thing repeats. It's gone through the data, the .bss. D goes first, E goes first, E goes next, then B and C comes up anyway. So basically, let's see what is happening. I should have what I should have done, which is what I didn't do. Reason why I printed twice is because I didn't get rid of this subroutine here. So if you want something clean, we are just about wrapping up anyway. If you want something clean, we run that. So the data.bss, then we've got the D, first in last out, right? We've got the E, then we've got the B, and then the C being printed. So now we notice that the stack starts to grow significantly as we use more nested functions. So basically, as we what we had before, we had these two functions really active. It didn't even affect the stack much until we started calling functions from within functions, and then our code starts to not look very efficient. Okay, I'm happy to bring the class to a close here, more or less officially, and you are going to get some stuff on using timers, using interrupts, and other things. Please watch the video and honestly try not to cheat. Right.